Hello, this is Mr. White, and this video is on the introduction to Radian measure. And I really need you to take notes on this one. This is the type of material that when you look back on it later in the chapter, you're going to realize how simple it really is. But it's also just so radically different from what you've grown up learning, if you are not already familiar with Radian measure, that expect that it's going to take a little while for it to just soak in. So take notes on this, please. I first want to start off by introducing you to a new variable which you are very likely not familiar with already. It's called theta. It is the Greek letter theta. And please call it by that name. Here it is written out, T-H-E-T-A. I'll write it a little bigger in case you're viewing this on a mobile device. But call it theta, please. It is not 0 with a line through it or something like that. I'm referring to this symbol that you see here. Again, that is a variable. It is not a constant. So unlike some of the numbers that you see down here at the bottom of the screen, 5, -2, those are constants. So is 0. So is the Greek letter pi. That's a constant. Phi, which represents the golden ratio typically, is a Greek letter constant. I is a constant. But theta is more like X and Y and A and B, that it will vary from one problem to the next. So get used to theta. It's here to stay. And we will always be using it in the context of angles. We'll call angles theta. So here it is in context. And I want you to think a moment, what's wrong with this picture? The thing that's wrong with it is a mistake. It's such a common mistake that I've seen geometry teachers be careless and make this mistake. And I hope what you're realizing, what you're thinking is, this angle here on the left is not 90, just 90, it's 90 degrees. It requires the unit of degrees. This one on the right is 45 degrees. And if you never made a very big distinction, or that wasn't considered a big deal in the past, it is now. I'm going to be very picky. If you mean degrees, you better put the degree symbol. You'll see why. You'll understand why more by the end of this video. And I also want to now say that degrees are really quite an arbitrary way to measure angles. Now there are some reasons why we've chosen 360 degrees, or why somebody a long time ago chose 360 degrees to represent a circle, but I want you to ponder this. Let me bring up my GeoGebra file here. Who is it that in the first place said 360 slices is going to determine degree measure? Think of other numbers that we tend to like to use. We like the number 10 quite a bit, so why didn't we cut up a circle into 10 slices and call each one of those a degree? Why don't we say a circle is made up of 10 degrees? Or if that's not fine enough, if that's a little bit too big, why not 100? Why didn't we cut up a circle into 100 little slices and call each one of those a degrees? Why 360? Well, historians have their reasons that they're pretty sure of, but in the end, my understanding is that nobody really knows with 100% certainty. And in that sense, I say that they're arbitrary. And they're also on the way out as far as you're concerned as a pre-calculus and hopefully a future calculus student. We are going to be doing away with degrees for the most part. Unsettling a concept though that may be, get used to it. So I want to bring you back to, as a means of introducing what we're going to replace degrees with, I want to bring you back to this geometry concept. That when you scale something up or down, or dilate it as it's sometimes called, remember how the sides change? But there are two quantities, main quantities that don't change. Notice as I'm scaling this up or down, the angles do not change, and neither do the ratios. So even and again, this is the idea of similarity or proportionality. That should sound familiar from geometry class. The ratios or the proportions do not change as you scale something up or down. So let me bring up another GeoGebra file. Here's an arc, or a sector, I should say. And notice that as I scale this up or down, I've got some measurements on there, that neither the radius represented there by r or the arc length, that's what this letter S is, that represents the arc length, that even though they are changing, their ratio stays the same. So right now, the arc length is half as long as the radius, and even as I scale it up, it is still half as long as the radius. And likewise, that proportion not only didn't change, but neither did the angle. So I could show you the angle up here, by the way, but I don't really care to. Again, degrees are on their way out. So the concept that we're going to replace degrees with is we're going to really focus on the ratio between that arc length and that radius. And right now, we would say that ratio is a 1:2 ratio, right? Arc length S divided by ratio R. That's a 1/2 ratio, no matter how I scale it. And that's the new way we're going to measure angles, believe it or not. We're going to say that that angle is 1/2. And if you're wondering, 1/2 what? Well, we could say 1/2 radians. That's the new word we're going to use. We could say it's 1/2 radian, but when we write it on paper, we'll often just write 1/2 without any units because it's really just represents a ratio. Pause this video and let that sink in if you need to. So let me go to this definition here. By definition, the radian measure of an angle is the ratio of the arc length S over R. And get used to using S for arc length. We will be doing that regularly. R, you're a little more familiar with that, being your radius. And again, the number of radians is going to be that ratio S over R. So let me bring theta in here. And we will typically say that theta equals S over R. But let me really stress again here that that only works for radians. This formula that you're seeing on the screen right now, make it very clear in your notes that that only works for radians. As soon as you start talking degrees, you try to slip back to your old ways, that formula does not work. Now, I want to point out that that formula can be rearranged. We've got theta equals S over R. I can easily rearrange that and say that S equals R theta. That gets S by itself. I can also try to get R by itself and say that R equals S over theta. So those are all saying the same thing. And this formula is our first piece of evidence of why radians are really preferable to degrees. It's such a simple formula relating angle, theta in radians, to the arc length to the radius. Now, if you're wondering, if you're thinking, oh, I want to go back to my old ways, I want my degrees. Well, there is a formula for that, but I'm never going to really acknowledge it in class. I want you to use the big boy and girl formula, S equals R theta. And where the book has the arc length formula for degree measured, I'm not even going to give it the dignity of showing what that formula is here. Please ignore it. Now, just to be clear, we will deal with degrees here and there, and we'll have a transition period where we're kind of dealing with both degrees and radians. But again, ignore that formula, that's that arc length formula for degree measure. We'll find another way to work around it in class. Okay, so again, old degrees on their way out, radians are coming in, they're the new thing, the new hot trend amongst the kids on the street. So let's put that formula to use, or this concept to use. I'm going to ask you, what is theta in radians? And again, hopefully you'll start to appreciate right off the bat how easy radians are to work with. Remember what the definition of a radian is? Ratio of arc length to radius. So hopefully you're thinking 7 over 5, or more specifically 7 inches over 5 inches, but you know that those units cancel each other out, and so it is fair to just say theta equals 7 over 5 and just leave it at that. If you want, if that really makes you feel uncomfortable to just say 7/5, you could say 7/5 rad for radians if you want, but that's really not necessary. You can just say 7/5. Or if you prefer, 1.4. Okay, example number 2. Here's a scenario in which I give you what theta is, and again, notice that I didn't put any units on it. It is a unitless quantity. So here I give you theta, and you are, and r, and you're asked for s. Well, let's use the form of the formula s equals r theta. And if we plug in the r and the theta, the 10 millimeters and the 0.3, we get s equals 3 millimeters. That is our arc length. Pretty simple, I hope you agree. Okay, how about this one where I give you theta and I give you s and I'm asking you to find r, the radius. So just to mix it up a little bit, I threw a variable in here. That n is a variable, that's not a typo. So 100 n miles is our value of s. And I'm not telling you what n is, but you can still deal with this. Here we would say r equals s over theta. And I hope you realize you don't have to really memorize all these different formulas. If it were me, I would just focus on s equals r theta. And then from there, you can, as soon as you write it down, it's pretty easy to see, okay, I can say r equals s over theta, which equals 100 n miles over 2.5. Well, we know, let's do this mentally, 100 over 25 equals 4, so 100 over 2.5 is going to equal 40 n miles. That is our radius. All right? So if that seems simple, if that seems something manageable, it is. And for the sake of those of you who view these on mobile devices, I've got these kind of crammed in here. I just noticed this is off screen a little bit. So sorry if this is a little bit cramped, but if you're viewing this on a mobile device, I want you to be able to see it. Pause the video at this point. Make sure you can fill in the blanks here, fill in the question marks. Okay, I'm going to assume that you have paused and verified that you can do this. Let me put the answers up here. For number 1, theta is 6 over 5, or if you prefer, you could have written that as a decimal, 1.2. I don't really care at this point. For number 2, s equals 6.3 feet. That was r times theta. And for number 3, the radius was s divided by theta, and that gives us 8 yards. Honestly, if you feel like you got this, feel free to stop watching at this point. You're good. But if for some reason you need a couple more exercises, I got one more page of them here. So here are 3 more exercises if you need to practice. But again, if you're good at this, you feel free to stop. Okay, I'm going to assume that you have paused the video and given this a try on your own. Question number 4, I'm using a unit you may not be familiar with, a furlong. That's equal to 1/8 of a mile. I'm going to be very forthcoming here. I did not really know how long a furlong was. I had to look that up. For number 5, r, again, that's s over theta. That would be 12 micrometers. That's what that little weird symbol means. That's micrometers. And number 6 here, AU, that's an astronomical unit, the average distance between the sun and the earth. In that case, the ratio of arc length divided by radius is 0.7 here. All right, if you had any questions, please make it a priority. Come by office hours. Radians are here to stay. You want to get them down as quickly as possible, so please make it a high priority. Get your questions answered on this material. Thank you.